which is to find a question in this kinematic space. So what is our kinematic space? One fact graph to define the color order. That's it. Now we have some rule for assigning momenta. Our objects are walks on this fact graph, which are the arcs or the laminations. That's our space. And in this space, we have to find a question whose answer is sum all the Feynman diagrams with the product of 1 over propagators, right? And ideally, then do the loop momentum integrals to get the final loop amplitude, right? That's what we're trying to do. All right, so that's what we're going to do in the rest of today. And just so you have an idea of where we're going, from now until lunch, I'm going to introduce the kind of more elementary, but sort of a very important backbone of the story, an object that we call the Feynman fan. You'll see what the word fan means there. This is not someone who's a fan of Feynman, which I'm not especially, because he was, while extremely brilliant, a little bit more than a bit of a jerk at the same time, and a sexist asshole to boot. But anyway, he did do a lot of great stuff, so that's you have to take the good with the bad. But anyway, so the fan means something else than being a fan. So we'll talk about that. But what this is building up to is a picture for the amplitudes, okay? For the actual amplitudes of the natural object. And we're going to see that the all-loop amplitudes in this theory can really be associated with a certain counting problem. Right, so I told you, again, yesterday in general, there's some combinatorial structure, blah, 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 blah. There's going to be a counting problem associated with these, with the arcs are going to be turned into some words. The words are going to have some counting problem associated with them. And different ways of treating that counting problem will get us the particle amplitudes and the string amplitudes. And we're going to see the string theory without ever having talked about strings, the world sheet, conformal field theory, blah, blah, blah. There is a surface, all right, it's this surface. It's the surface on which the diagrams are drawn, and this surface is going to turn into the other surface, okay? And as we'll see, the set of objects we're talking about is actually a little bigger than, it's going to be the bosonic string theory. It's going to be a little bigger than the bosonic string theory. One sort of corner, one very special, important corner will be the bosonic string, but it's a broader set of objects that we're allowed to talk about. So we'll see how much of that we get to, but I'll certainly try to get as far as telling you what the sort of particle limit of all of this is. And in particular, we don't ever have to talk about strings if we don't want to. The fact that there is a global unified object, so this is going to be a picture of amplitudes that you can think of as associated with a certain form of global Schwinger parameterization. This is something that has nothing to do with strings. Okay? It's something that's sort of built into the combinatorial problem that I'm telling you about. And there's something already stringy in this sense already about the particles, okay? It's just that in this way of thinking about things, they're so achingly closely related to each other that when you see the fan picture, you'll immediately see the string picture is going along with it, okay? All right, but this is what we're going to do now. And we're going to begin with the most basic question. Again, recapitulating the question that we had from yesterday. We've seen that our kinematic space is associated with one diagram. So the most zeroth order aspect of the question of where the rules of space-time and quantum mechanics are going to come from is why would we ever think about all the diagrams? What would ever make us think about all the diagrams? That's one question. Second, why do we have to put them together? Why do we have to add them all up with uniform weight, with the same weight for all of them, right? So these are the two most basic aspects of this challenge. And the beautiful thing that we're going to see in this lecture is that the answer is just lying in plain sight. Okay? We're going to see something magical happen that answers this question when we simply think about how to explicitly label the curves on the surface, the arcs on the surface. Okay? Once we just think about how to actually, again, imagine you're blind and you can't see, how you would tell someone what the arcs on the surface are. When we do that, we'll see that it just gives us an answer to this question. There is an object, the Feynman fan. We'll see that every diagram is associated with some cone, and these cones together tile the entire space. And so there's no way to to leave one of them out, all of them come to life, and you have to keep all of them together in order to sort of cover the entire space that we're seeing in a natural way. And this, of course, gives us new ways of computing the amplitudes, representing the amplitudes, and when we get back in the afternoon, we'll see that this picture suggests a way of doing global Schwinger parameterization. Now, for the second picture, for this global Schwinger parameterization to be practical, we're going to need a way of characterizing this fan, and that's where a second interesting thing happens. So there's sort of two little miracles in this business. One of them is that the fan exists. The other one is that there is a way of characterizing the fan that's really remarkable that exists in an conceptually interesting and very practical way, and that's going to allow us to give concrete formulas for the amplitudes. I'll show you what some of the formulas look like in the next lecture, okay? But I just want to stress, this picture is fundamentally about particles. The two-dimensional surfaces that we're talking about are just the surfaces that we talked about before. They're the ones that associate with the topological expansion. But this is going to hand us this generalization from particles to strings without making any reference to a worldsheet, CFD, vertex operators, etc. The whole subject is a fundamentally more combinatorial origin for both particle and string amplitudes. Okay. Okay, so let's get back to Earth, and we're going to talk about labeling the curves on the surface. And let me begin with a slightly more interesting example. 5-point tree amplitude. Okay? Now, remember, all of our variables are roads, are paths on the surface. Let me make one little point. And what is a path? A path is I just walk, right? There's only one rule that I want to add in order not to deal with with a trivial redundancy, which is the rule is that there are no U-turns. So once you walk down a road, you can't stop in the middle and walk back along the road, okay? There are no U-turns, you just have to keep walking. So once you hit a road, you've got to keep walking until you hit the next intersection, and then you get to choose whether you turn left or right at the next intersection, and you keep on going, all right? This, in the surface language, is called being in minimal position, and it's meant to avoid kind of dumb things like this. Like you might have if I say it in the language of a surface, you might imagine something, you might imagine like a lamination where you do this, right? And that's sort of really dumb because you're just going back and forth, back and forth, back and forth, not doing anything. Okay, so we're not allowed to double back along the roads. Okay, but modulo that, every curve that you draw, every road, every path that you take on the fact graph counts as some possible variable in our problem. Okay, and they're all assigned momenta. So again, this is what's called being in minimal position in the kind of surface literature. All right, so let's take a path. So here's a path. Oh, and let me again label, for convenience, I'm going to label my roads. This is road 1, 2, road 2, 3, 3, 4, 4, 5, 5, 1. This is road 1, 3, and road 1, 4. All right. Now, beforehand, again, when we were talking about things yesterday, we just immediately would have called this, what would we have called this yesterday? We would have called this x25, right? So yesterday, we would have okay, so this is something that's going from a little bit to the right of 2 to the little bit to the right of 5. So this is a curve we would have called, the chord we would have called x25 yesterday. And yesterday we had no problem just labeling it 2,5 and saying, oh, it's obvious, you start the picture and so on, right? Today we're being more humble, okay? We can't see anything, we can't draw the picture, we have the fact graph, right? And so how would I describe this curve? Okay, so suppose you gave someone the map of a fact graph. There's a map. and you wanted them to take this yellow trajectory, this yellow route on the fact graph. How would you label it? How would you tell them what to do? Well, we're going to imagine that we're Google Navigate, okay? We're just going to do Google Navigate. I'm sorry to shill for Google here. Sorry. I wish there was another company. We're going to imagine that we're just going to following rules, right? So what's the Google Navigate for this curve? Well, I'm starting on the road 2, 3, okay? Then I make a left turn onto the road 1, 3. So I'd say left onto the road 1, 3. Okay? Then what? Then I make a right turn onto the road 1, 4. Okay? Then what? Then I make another right turn onto the road 5, 1. Right? So this is what we're associating with what we were calling 2, 5 before. There is a following word. So the word for this, what I was calling 2, 5 before, there's this word, 2, 3 left, 1, 3 right, 1, 4 right, 5, 1. Okay? And clearly every curve has a word like this. Now, for just the typographical purposes, because it looks a little bit nicer than writing L's and R's, I'm going to write this as a little mountainscape. Okay, so left I'm going to denote by making a left turn as going up, right by making a downturn going down. So this is just so I can draw it more nicely on the board. So it's going to be 2, 3, left to 1, 3, right to 1, 4, left to 5, 1. Okay? 1, 5 and 5, 1 are the same. That's right. And I could have called it 1, 5, but yeah, I just labeled it here 5, 1. I could have labeled it A, B, C, D, E. It doesn't matter, right? So I'm just labeling the roads somehow. All right, so let's actually now draw. In this case, I really want to draw how many curves are there? The total number of curves in this picture. How many are there? Sorry? Oh, sorry, down. Sorry about that. Thank you. Sorry, did I go? Yes, down. I'm sorry. Thank you. Sorry about that. Okay. So how many curves are there in this problem? How many walks are there in this problem in total? There are 10 walks in this picture. Okay. So what are the 10 walks? There are 5 boring ones that are just the boundaries, and 5 more interesting ones. Okay. So actually, once and for all, just so we do it, you'll be slightly bored. Let me just write out all 10 words for all 10 curves. All right? Okay. We're going to learn a little something from it. Okay, so first, oh shit, why did I erase? That's exactly what I should not have erased. Okay, so let's first do the boundary ones. Okay, so there's this one. So like 1, 2, 2, 3. Let's do these ones first. So what does I'll put the ones in quotes. What does 1, 2 look like? Well, this is pretty boring. It's 1, 2, left, 1, 3, and then left, 2, 3. Right? And let's keep going. What does 2, 3 look like? Well, you see, these are all boring because they're all just turning left forever. Right? So 2, 3 is going to go 2, 3, left on 1, 3, and left on 3, 4. Okay, and 3, 4. This one is going to be 3, 4, left on 1, 4, left on 4, 5. 4, 5 is 4, 5, just left on 5, 1. And finally, what I would have called 5, 1 or 1, 5 is 5, 1, left on 1, 4, left on 1, 3, left on 1, 2. Okay? So those are the boring ones. And now let's do the more interesting ones. There are 5 more interesting ones. So there's what we would call 1, 3 before. So 1, 3 would start here a little bit to the right of 1 and go to a little bit to the right of 3. Okay? So this is 1, 3. So what is 1, 3? This is 1, 2. I make a right onto 1, 3, and then a left onto 3, 4. All right? Let's do the next one, 1, 4. These are the ones that happen to correspond to the chords that are in the triangulation. So this would be here, like this, right? So that is 1, 2, and then I make a right onto 1, 3, and then another right onto 1, 4, and then a left onto 4, 5. Okay, then let's do 2, 4. So 2, 4 does this. Okay, so 2, 4 is 2, 3, and then I make a left onto 1, 3, and then a right onto 1, 4, and then a left onto 4, 5. Let me do the rest here. 2, 5 is the one we did before. So 2, 5 is 2, 3, right onto 1, 3, left onto 1, 4. Sorry, left onto 1, 3, right onto 1, 4, right onto 5, 1. And finally, what's 3, 5? 3, 5 is like that. So 3, 5 is 3, 4, a left onto 1, 4, and a right onto 5, 1. Okay? Yes? Sorry? Oh, I'm sorry, because I did it wrong. Thank you. Sorry about that. Thank you. Okay? So far, so good? So, 10 curves, 10 words. All right. So far, so boring. Now, we're going to, these words clearly tell you exactly what curves you are talking about. And by the way, how could you generate every word? You just do it on the computer, right? It's a decision tree. You just go everywhere, you either make left or right, you just keep on going forever, right? Sometimes you'll get a finite number of things, you'll just exit. Sometimes you might keep going forever. The surface gets complicated, but it's zero thinking, right? You go, every word you can just generate. It's a giant decision tree. You just turn left, right, and every one of those corresponds to some path on the surface. Now, we're going to actually take an even slightly coarser measure of these words. It actually turns out to be exactly the same content, okay? But I'm even going to forget about whether you're turning left or right, okay? I'm just going to record for every curve, for every arc, something known as its geometric vector, right? So for every curve C, I'm going to define the geometric vector geom of C. I told you this is something for people in junior high school, and I'm proving it by using vector signs. See, I'm not so cool that I don't use vector signs. Okay, so when vectors are vectors, they have a vector sign on top of it. I'm not an index-free guy. Okay, so all right, so it's a geom vector. But what is this vector? It's just recording what are the roads in my problem. The roads are 1, 2, 2, 3, 3, 4, 4, 5, 5, 1, 1, 3, and 1, 4. I have 7 roads in my problem. So for every curve, I'm going to record a 7-dimensional vector. An integer vector that just records the number of times my curve hits that road. All right? So in this case, my basis is going to be, it's a 7-dimensional vector. So we're going to take a little bit of time writing them. Okay, so in this basis, the geom vector is just going to be just telling me the number of times each road is encountered. In this case, it's a vector just of 1s and 0s, but you might imagine in more complicated curves, it could have this winding around, spiraling, doing stuff. It could have some interesting larger integers in it, okay? All right, so for example, let's look at the various geom vectors here again. just to give a quick example. So for example, the geom vector for 1, 2, note, here's an important point. This is a geom vector for the curve 1, 2, for the arc 1, 2. So it is not 1, 0, 0, 0, 0, right? After all, what is the arc 1, 2? It's 1, 2, 2, 3, right? So the geom vector for this guy is 1, 1, 0, 0, 0, 0, 0. Okay? The geom vector, let's do another one. The geom vector for, I don't know, 2, 4 is, 2, 4 is a juicier one. 2, 4 is 0, 1, because it has a 2, 3. And it has a 0, 0, 1, and then 1, 1. Okay? No. You mean 5, 1? No, that's right. There's no left or right here. So I'm just counting the number of times you hit any road. As I said, it turns out this information is, it doesn't lose any information. But for now, we're just doing it. Okay? Yes? In this case, it's redundant. In this case, and if you think about it a little more, it's redundant in general. But here, it's totally obviously redundant. Okay, so once you know where you're going, it's clear how to get there. You can only turn left or right. When it gets more interesting, when there are bigger integers, you might think that you can hit it in different places along the trajectory. And it's slightly more non-trivial that it doesn't matter, actually, that the geom vector contains all the information. But here, it's obvious that it's the same information. Yes? Yeah. Did I invert? This was 0, for which one? For this one, I did 2, 4. Oh, that was 2, 5. Sorry, I was copying down 2, 5. Sorry about that, okay? I was copying down 2, 5 from the end there. That's right, if we're doing, yeah. So, good, let's do 2, 4 literally, was 2, 3, that's right. So I wanted to have 0, 1, and then 1, 1, okay? Sorry? Oh, sorry. 1, 0. Thank you. 1, 2, 2, 3, 3, 4, 4, 5, 5, 1. So I'm supposed to have a 4, 5 in 2, 5 there. In 2, 4. I'm supposed to have a 4, 5, so that's the 4, 5. Okay, and that's 1, 3, and 1, 4. Okay, so what I now have is 10 curves and 10 7-dimensional vectors, right? So if I want to know what is my entire big kinematic space, I have now described my entire big kinematic space is in a 7-dimensional space. I have 10 7-dimensional vectors. So far, so good? Right? Still, so far, so boring. Nothing is happening yet, right? Classic kind of lame mathematician thing to do. Okay, who cares? Make these vectors, big whoop, all right? But now something magical is going to happen. The first magical thing. We're going to do something which in this context is the analog of going on shell. Okay? We have not put in something yet here in this picture, which is that the external boundary guys are somehow on a different footing than the internal ones. The external boundary guys are not honest variables. The internal ones are, right? So we should somehow ignore the information about the external ones and only keep track of the information of the internal ones, right? So that means that I have these 5 vectors that correspond to 1, 2, 2, 3, 3, 4, 4, 5, 5, 1. I somehow don't want to keep track of them. I only want to keep track of the rest of them. Okay, so that's the analog of sort of going on shell. Now, how do you think you would do it? Let's say someone handed you this 7-dimensional space of vectors, right? And they said, look, 5 of these vectors, the one that corresponds to geom of 1, 2, 2, 3, 3, 4, 4, 5, and 5, 1, those 5, I don't want to think about them. I want to ignore them. What's a canonical way of ignoring things in linear algebra or when you have vector spaces? How do you ignore something? You take the quotient, okay? Now, what does it mean to take the quotient sort of geometrically? So you have some configuration of vectors. You have some 3-dimensional vectors, this vector, that, right? You want to ignore this vector. What does it mean? You project. It means you'll stare in the direction of that vector. Right? When you stare in the direction of the vector, what happens? The whole picture goes down one in dimension, and the vector you're trying to ignore gets mapped to the origin. Okay? That's what we're going to do. We're going to take this 7-dimensional picture, and we're going to project through 5 of the directions. Which 5? The directions for geom 1, 2, 2, 3, 3, 4, 4, 5, and 5, 1. Okay? All right, so we're going to be left with a 2-dimensional picture in the end, right? Because we had a 7-dimensional picture. We are projecting through 5 directions, so we're going to be left with a 2-dimensional picture. Let's say a little bit more about the 7-dimensional picture. Again, nothing very special about it. I just have 7 vectors. They all have positive coefficients. They all live in some upper orthant, right? Nothing very special seeming about this collection of vectors. Now we're going to project. And I won't just do the algebra in real time, but I'll actually tell you, how to do the projection is very simple. It's a 7-dimensional space, so I can write all the vectors as a linear combination of 7 of these vectors. So I'm going to choose 7 of these guys and write the remaining 3 as a linear combination of those 7. Which 7 should I choose? I can choose any 7 that I want. It's just a basis choice. Of course, it's natural to choose the basis to be 1, 2, 2, 3, 3, 4, 4, 5, 5, 1, as well as 1, 3, and 1, 4. 1, 3, and 1, 4 are the things that kind of occur in this triangulation. And if I do that, I'll leave it for you to do the linear algebra exercise. But you can easily see that the geom vector for the other 3, for 2, 4, is equal to the geom vector for 1, 4 minus the geom vector for 1, 3 plus the geom vector for the boundary, 2, 3. Geom of 2, 5 is minus geom 1, 3 plus geom 2, 3 plus geom 5, 1, and geom 3, 5 is minus geom 1, 4 plus geom 3, 4. Okay? That's just the linear algebra. You can just check that they're all expanded in this way. Okay. Now, I wrote it this way because this makes it very easy to do the projection, right? Because when we project, what's happening is that all of these boundary guys are just going to 0 under the projection. And so this just tells me how to express, I now have 5 vectors left, right? All the boundary guys have gone to 0. So I have my 5 vectors, 1, 3, 1, 4, 2, 4, 2, 5, 3, 5. And I'm now telling you how to express these 3, 2, 4, 2, 5, 3, 5 in terms of 1, 3, and 1, 4. There's a tiny pause here. Note the parallel with something that we talked about yesterday when we were talking about the isosahedron and solving the wave equation. We're solving for all the x's in terms of some basis set that corresponded to the past boundary, 1, 3, and 1, 4. Okay? And I told you the picture we're talking about is kind of a dual of the picture we're talking about yesterday, and this is where there's a commonality. Again, we're choosing a basis. The basis is a choice of which triangulation that I started with. Once I make that choice, it's natural to choose a basis, and this now gives me a way of recording what the picture looks like at the end. So now let's look at the picture that we get in the end. And then after we do this, I'll tell you a shortcut for getting the answer that doesn't have to go through any of this little linear algebra. Okay? But fundamentally, it's all about these geometric vectors and projection. So let's draw the picture. So In my two-dimensional space, I have the, oh, sorry, after projection, these geom vectors are called G vectors. That's just the name that we're going to give them. Little g vectors instead of geom vectors. Okay? So these little g vectors in this example are two-dimensional vectors. All right? And let's plot what they look like. Well, I had my basis. So here is 1, 3, and here is 1, 4. That was my basis to begin with. Right? So now let's look at the rest of them. Who's 2, 4? 2, 4 is 1, 4 is going to be the g vector for 1, 4 minus the g vector for 1, 3. Right? And the rest got projected away to 0. So 2, 4 is this guy. Okay? Who's 2, 5? Minus the g vector of 1, 3. So that's 2, 5. And who's 3, 5 is this one. Okay? Now, this kind of picture, so notice one interesting thing already. Now we have a picture that kind of tiles and covers the entire space. Okay, we didn't have that before. We just had a bunch of cones with positive coefficients, right? They all lived in some positive orthant. After projection, we have something that covers the whole space. And any picture like this of a bunch of sort of cones that cover the whole space is called a fan. Okay? So this is called a fan. Kind of because it looks like a fan. You know, it looks like a fan that you... All right. But now something wonderful has happened here. Okay? Something quite... And here you might not be so impressed, but you'll be more impressed as we see more complicated examples. Remember, what have we put in so far? We've put in the one triangulation that defined the surface that we're talking about. We recorded the vectors, and we went on shell, quote unquote, by projecting through the boundary components. Okay? Now we get a picture of some cones that tile the whole space. But let's just go back and draw these, pretending that they're chords, just so I can draw them a little bit more easily. 1, 2, 3, 4, 5 in here. Well, who are these guys? Well, no surprise, these were the triangulation of the surface to begin with. Okay? But what's going on in here? Who do I see here? I see 1, 4 and 2, 4. Another triangulation. Who do I see here? I see 2, 4 and 2, 5. Another triangulation. Of course, I see every triangulation, every Feynman diagram. In other words, 2, 5 and 3, 5. Here's 2, 5 and 3, 5. And 1, 3 and 3, 5. We didn't ask for it. We just recorded the damn data of the curves. We went on shell, and it just produced for us all the Feynman diagrams. Okay? It divided the space up into pieces, each piece associated with a Feynman diagram. And furthermore, they all touch each other and they tile the whole space. So you want kind of a very zeroth order answer to the question, why do we care about all the diagrams and why should we combine them all together in some democratic way? We care about them all because that's what we get from the kinematic space when we go on shell, and we have to combine all of them because that's what it's telling us to do, right? We can't put any holes in the space. You need all of them to cover the entire space. Okay? So in this way, very vividly, you know, the sort of need for all the space-time processes, which is all the diagrams, which is the same as all diagrams. And why add them all together? for quantum mechanics is the same as the completeness of the fan, the fact that it doesn't have any holes. But it emerges just immediately from essentially doing nothing other than recording the information about the curves and projecting through the boundary components to do the analog of going on shell. Okay. Now, before we keep on going, I want to tell you the shortcut rule for getting the g-vectors. And I'll leave it as a little exercise for you to prove that this rule follows from the projection. This works for any surface, any number, for any surface at all. And the rule is the following. Look at the word, and let me write the rule now. Sorry? I'm not. Which diagram? Which? Oh, they're not diagrams. They're curves. I'm ignoring the curves that correspond to just the boundaries. Okay? Well, because they don't. The ones there's an asymmetry between the ones on the boundaries and ones on the inside. The ones on the inside can actually vary. They're part of the dynamics. The ones on the outside are locked by the on-shell conditions. They're just given by the mass squareds of the particle. Okay? So that's why I said it's like going on shell. The curves on the outside, their p squared is equal to m squared. They can't vary. The ones on the inside can. So we need to input some asymmetry between the boundary curves and the interior ones. And the asymmetry is just projecting through them. Does that answer your question? Okay. All right. So in general, the g-vector for any curve is given by the following formula. You sum over all the valleys minus the peaks of the word for C. Okay? So let's see that it works. So first of all, it's very nice. Let's look at the boundary curves. Boundary curves have no valleys or peaks, so they're 0. That's good. They're projected to 0. Right? Okay, let's look at this guy. 1, 3, it has exactly one valley, which is 1, 3. So the g-vector for 1, 3 is 1, 3. The g-vector for 1, 4 is 1, 4. The g-vector for 2, 4 has a valley 1, 4 and a peak 1, 3. So it's 1, 4 minus 1, 3. Okay? The g-vector for 2, 5 is minus 1, 3. The g-vector for 3, 5 is minus 1, 4. Okay, so that's why just by looking at the words, you can just instantaneously write down what these vectors look like. Okay? Okay? I leave it as a little exercise for you, as I said, to prove this rule. Very simple to prove it. It's just a little bit of linear algebra, but it's slightly cool. It has to do really to the fact that what's special about the boundary curves is exactly, no matter what, they always turn left. So you have a linear projection whose job is to kill, always turns left. And a projection is totally defined by its kernel, and the only linear object that produces always kills left is this peak and valley rule. Okay? You can show that quite easily. Just a little bit of linear algebra. All right, let's do another example. So this is at tree level. Let's do a one-loop example. All right, so we're going to do a bubble diagram. So this is going to be my fat graph. And this is going to be my corresponding surface. I'm just drawing the surface picture just for fun, okay? Let me label my roads alpha, beta, I don't know. What did I do here, just so I don't screw up my notation? B and A. Why did I do that? Okay, I'm just stupid. All right, that's fine. Okay? What are the roads that we have in this picture? Well, we have, let's draw it on the surface first. So we have these two guys that we drew. These are the chords. So there's going to be two laminations, two arcs associated with either one of them, where you spiral around one way and spiral around the other way. So there's 4 of those guys. And I have 2 more chords that I could draw, and then also the arcs. I have this variable, and I have that variable. Okay, what are those variables? Those would be the tadpole propagators. So, for example, here's another triangulation I could have drawn, just to draw in the language of diagrams. So here's a triangulation. Again, it's a very funny triangulation, but it's a triangulation, and it corresponds to this fact graph. Okay? And so this propagator corresponds to that one. Okay? Meanwhile, this propagator corresponds to that one. The loop guy. All right? But once again, let's look at our various curves. I'll do some of them. So, for example, what is the curve alpha? Goes around like this, and this is going to be one that spirals forever in that direction. Okay, so let's write the word for this guy. So the word is alpha, and then it makes a right onto A, right? And then a left onto B, and then a left onto A, and then a left onto B, and a left onto A forever, right? So if I call this, okay, so that's one of the curves, and it would correspond to let's say, depending on how I label alpha and beta, it would correspond to one of these spiraling curves that's spiraling counterclockwise, like that one. Okay. What about the one that spirals the other way? The one that spirals the other way would be alpha, and then I would do this way, B, A, B, A. So this would be alpha, left onto B, right onto A, right onto B, right onto A forever. Okay? So that would be the curve that spirals the other way. Finally, let me do the curve that just would go around like this. Okay? So that corresponds, I'm drawing them as arcs, as chords, but we could draw them as, here on the fact graph, I'll just draw it here. This would look something like this, right? Comes around, comes back to the same spot. Okay, so this would look like alpha, beta, BA. Something that looks like alpha, right on A, left on B, and then right back on alpha again. Okay, yes? Sorry? Oh no, this is great. This only has a value and nothing else. Okay, so indeed, it doesn't have any other peak. That's right. Yeah. All right. So this guy's g vector for this curve is negative A. This guy, is positive A. This guy's g vector is negative B. This guy's g vector is A minus B. Okay, by our peak and valley rule. Okay. And similarly, we have the other ones from the top. So we have a total of 6 curves in this problem. And now let's draw them. Okay, so my basis curves here the A and the B correspond to this curve, and this curve up here, the one that spirals around counterclockwise this way, this would be exactly the same, everything flipped over, so the G vector for this guy would be B. So my picture looks like this. I have A and B. This corresponds to this curve. This corresponds to that curve. All right? Then I have this guy, which is A minus B. Right? So here's A minus B. That corresponds to this curve. And then the rest is just given by symmetry. So this guy here corresponds to the curve from the top. Okay, so that's B minus A. And then I have these curves. This guy corresponds to the curve from the top, but going, you see, this is the curve from the bottom, but going clockwise. That's this guy down here, is the same as the curve from the bottom, but going, this was going counterclockwise. This is going clockwise. And this is the curve from the top going clockwise. Right? So this is my fan now. Once again, the space got divided up into a bunch of pieces. But now, once again, let's look at what each one of the cones looks like. So this cone looks like, if I go back to drawing the chords, again, just for convenience to draw the picture, it looks like that triangulation. Right? This cone is bounded by these two curves, the one from the top and the one from the bottom, both of the same spiraling type, both of the counterclockwise spiraling type. Okay? This one here is the guy from the top, and this one. This one here is the guy from the bottom, and this one. Right? On the other side, I just get exactly the same picture, except the spiraling around for the curves is the opposite. Okay? So sometimes people in this business will draw a little hashtag, a tag on the line when it's spiraling, let's say, clockwise. Okay? So by convention, or we could put a plus and a minus. But here, I'm just going to draw this without a tag, and the ones on the other side I would draw with a tag. So here's a little tag to just remind myself that they're associated with the thing spiraling the other way. But here it's the same thing, but this guy is spiraling the other way, and here it's spiraling the other way. So you see a couple of nice things. Once again, the cones are Feynman diagrams. Okay? Maximal collection of non-intersecting curves. If I drew them as diagrams, this is this diagram. This is this diagram. And this here is the one up top. Okay, so there are three diagrams in this case. And the ones on the bottom are just, this is a symmetry plane. So we can reflect everything on the bottom. So I never get anything with the tags and the untags together. Okay, so there's this sort of doubling that I'm naturally getting. I could only keep one half if I wanted, or only the other half if I wanted. It doesn't matter. But the same thing happened. Okay, so all we do is we record the vectors. We project, and the space is automatically divided into cones, which correspond to Feynman diagrams that cover the entire space. Okay? Any questions about this? Yes. Ah, excellent, excellent, beautiful. If you start with a different fat diagram to begin with, then you'll get different G vectors. Okay? It's actually a nice exercise. You could start, for example, with this one, and you'll get a different picture of the G vectors. They're not even related by linear transformation. There's not like a linear transformation that takes you from one picture to the other. But if you like, the combinatorics is exactly the same. The pattern of things that come together, what the cones are, is exactly the same. We'll see this a little bit more explicitly in a bit. The pictures are related by a piecewise linear transformation. Okay? So it's a linear transformation which isn't a uniform linear transformation everywhere, but it's a different linear transformation from cone to cone to cone. So in other words, there's a linear transformation that maps any cone to any other cone, but there'll be a different linear transformation. So it's a linear transformation that's not linear everywhere in space, but it's a function that's piecewise linear. That's a different linear function in every cone. So this is a ubiquitous feature of this subject, and when we come back, or maybe even now before lunch, the words tropical is going to start making an appearance. So tropical geometry, and we're going to see this phenomenon of piecewise linear transformations everywhere. Okay? But that's a great question. If we start from a different base triangulation, we don't get the same g vectors, and so the entire subject has some dependence of the base triangulation. Okay? So that's something we could have commented on also yesterday, that when we defined the icosahedron, we chose a particular chunk, a particular way of choosing the variables in my kinematic space-time. I could have done different ways, different right triangles, or even different shapes, and I would have gotten different specific realizations of the icosahedron. But the combinatorics would always be the same. The pattern of how the facets meet would have been exactly the same. Same thing is true here. The pattern in how these things meet would be exactly the same. Now, maybe here's a good point to make contact with what I was telling you yesterday and say another aspect of this word fan, and also to explain the sense in which what we're doing today is dual to what we're doing yesterday. So that little picture there, our first little fan, yes. Yes, and the ABCs in the triangulation don't have to be distinct. Okay, so when you're defining, the combinatorial rules for defining a triangulation is just A, B, C. No one says A, B, C have to be different. You're even allowed to have the same edges. Okay, so the only rule is that you have I should have said that, thank you, before. The only rule is you have a collection of ABCs such that any given guy occurs, if any given guy occurs twice, it has to occur one with a lowercase and one with an uppercase. Exactly. It would be an A, little c, capital C. Exactly. So in this case, if they occur in the same triangle, they have to be, and that's exactly telling you that you're gluing the two legs of the triangle to itself. Right? Yeah, exactly. That's really the sort of point about these more degenerate triangles that's nicely dealt with this way of defining a surface. Okay? Yeah. Okay. So, yes. So I wanted to tell you something about how it's related to the picture from yesterday. Imagine we take this picture for various reasons. Well, let me draw it like this. So take this and imagine to every vector here drawing a normal to it somewhere. Okay, so I'm going to draw a normal here, a normal there, normal there, normal there, and normal there. Okay? Does that picture remind you of anything? That's exactly what our pentagon looked like yesterday. Okay? And in fact, this fan is known as the normal fan of the icosahedron that we talked about yesterday. The normal fan for any polytope is the following. You take every facet and you draw a normal vector for every facet, right? Every facet has a normal vector, actually a direction. I don't have to give the overall, just the ray that goes on with the direction. Let's say by convention, inward pointing, okay? Inward or outward, you choose some convention. So every facet is associated with a vector, right? So in this way, given a polytope, you get a collection of vectors out of it, right? This is clearly a dual collection of vectors, because the vectors are associated with not the vertices of the polytope, but the facets of the polytope, right? However, if you're given the polytope, a bunch of facets will come together to meet at a vertex. What does that mean? So for example, here, I have this facet and that facet. This one is associated with this vector, this one is associated with that vector. This vertex in the middle belongs to both facets. So that vertex is associated with a cone in this space, right? The cone that corresponds to the facets that come together there. Okay, so you see it's dual. The low-dimensional things in the polytope, like the vertices, are the highest dimensional objects in this fan. They're the sort of cones in the fan. Meanwhile, the facets of the polytope are the rays of the fan. Okay, so for any given polytope, there's something known in its normal fan, and it's just what we talked about. What you get by drawing the normals to all the facets, and the rules for who the vertices are tell you, if someone just hands you, in 2 dimensions, there wasn't anything to do. So this is why this example was a little bit of what made things a little simpler than in general, because if I just plop down a bunch of 2-dimensional vectors, it's unique how they divide the space up into cones. But if you think in 3 dimensions, if I hand you a whole bunch of 3-dimensional vectors, there's lots of ways you might imagine grouping them up into cones, okay? So when I'm telling you that the Feynman diagrams are cones, that turns out that's a canonical way of grouping them into cones. Okay, so that's a non-trivial fact that the ones that correspond to Feynman diagrams give you cones that tile the entire space. But you need more than the information of just what the normal vectors are in general. You need the information of also the normal vectors and who the cones are. Okay, so if someone hands you a polytope, then they've given you all that information. You get the normal vectors, and you also know how they come together into cones. And all the lower dimensional things, all the dimensional things in between, right? Any number of facets will come together to meet on some lower dimensional facet of some dimensionality, and that will correspond to some collection of the rays that come together to make an intermediate dimensional cone, right? But it's dual in the sense that the top dimensional things in this fan world correspond to vertices, the lowest dimensional things that are rays correspond to the facets of the polytope. Okay, so this story is kind of a dual presentation of the same kind of information that we're talking about yesterday. Except I'll tell you now, I won't spend much time explaining it, that knowing that you have a polytope is strictly more information. It's possible to have a fan. If you have a polytope, you get a fan out of it. If you're given a fan, it's definitely not always the case that you can associate a polytope to it. And the first examples begin in 3 dimensions, and it's a very fun exercise to try to build a collection of vectors and cones that go along with them that you cannot realize polytopally. Okay, so there's a classic counterexample, but you can, it's not totally trivial to find it. It's a little bit fun exercise to find it. So knowing that it comes from a polytope is strictly more information, but for today, we're going to be concentrating entirely on the fan. Okay. Now, before we stop for lunch, let me tell you some generalities about this Feynman fan. Okay? Some of the things that we're not going to get to talk about in more detail. One, in general, the fan is infinite. This is the infinity that I keep referring to. And let's see our first example. Our first example is the annulus, just this very simple example, okay? The surface that goes along with it, drawing the surface, is this one, and the infinity is just what we talked about. You have this curve, you have this curve, you have these curves that wind around any number of times, okay? So what is a Feynman diagram? There's just one Feynman diagram here, and it's just this guy. Okay, but there's infinitely many cousins of this guy, where you just twist the inside as much as you want. Okay? But let's see what the g-vectors look like. So let me call this road alpha, A, B, and beta for this one. So for example, this curve, oops, I guess I could have gone, call this A and B. This curve is alpha, right A, left beta. Okay? Let me wind around one more time. So what is this? This is alpha, right A, right B, left A, left beta. Right? Now what happens if I keep going? Let me wind around one more time. Then I'll have alpha, right A, right B. I did alpha, right A, right B, left A, left beta. Yeah, if I do one more, then it's alpha, right A, right B. Yeah, except instead of going back up to beta from here, so I'm going to do A. Instead of going right to eta again, I'm going to do left to beta. I'm going to do a right on B again, left on A, and left on beta. Okay? As you see, as I wind around more and more, I'm just going to do this BA, BA, BA a bunch. Okay? So what do the g-vectors look like? So let's just do our peak-valley rule again. So I have A, this is the first one, and then I have B. But the next one that winds around one more is the same thing, but still a B, 2B minus A, right? So the next one looks like this. The next one looks like that. I keep on going, right? I keep adding B minus A, because the going back and forth is keeping adding B minus A. If you do the ones that wind around the other way, I'm going to get this one, and then it's going to do the same thing. It's going to keep going in this direction. Right? Okay, so is that clear? So I have positive winding variables, if you like, and negative winding variables, and they differ by multiples of this B minus A. Right? Okay, so this is cool. What I was telling you before is almost exactly correct. Again, I have cones. They cover the entire space, almost. Well, in this case, every cone is a diagram. It's kind of trivial because there's only one kind of diagram. Okay? But do they cover the entire space? Almost. They cover the entire two-dimensional part of the space, but there is one direction that they miss. They're never going to hit this line minus 1, 1. That ray is not going to be contained in any of these cones ever. Okay? So that's a little bit interesting. We started off our whole story by thinking about curves on a surface. Everything is great, magical. You project through, you get complete fan diagrams, blah, blah, blah. And now we find that beginning with the annulus and forevermore, there are some lower dimensional parts of the space that are not quite being covered. Okay? So you might think, oh, you don't care that much. It's mostly being covered, but there's some funny lower dimensional parts of the space that are not being covered. Do those parts mean anything? Okay, well, they definitely mean something. This guy is actually the g-vector for a curve. Okay, any guesses? What curve have we not drawn on the surface that we could have drawn? So let me draw the annulus again. I'll draw it back as a surface, and we'll also see it on the fact graph, of course. Okay, so here's my annulus. We're so obsessed with Feynman diagrams for our trace phi cube theory, we are only drawing a bunch of curves that correspond to propagators for the trace phi cube theory. Is there a curve that I could have drawn that I have not drawn? just a loop. The closed curve on the surface. Okay? Right? Now, what's the g vector for this closed loop? Well, there it is. So what is its word? It's b, down a, up b. Well, you just keep on going, but it comes back to itself, right? So the g vector is exactly a minus b. So we call this curve delta, and its g vector is exactly a minus b. Okay? So we're missing that guy. If you add it, then everything is covered. Right? Then the entire space is indeed covered. Now, what do I mean, add it? What I mean is that when we talk about triangulations of the surface, we should allow ourselves, when we say maximal collection of non-intersecting curves, we should allow ourselves to add closed curves. Okay? If we add closed curves as well, then we get different kinds of triangulations. Some that contain only the open curves that we talked about before, some that also contain closed curves. Okay? This is a very small example, but in general, the claim is that if you include all possible triangulations, including the ones that have closed curves in them, then that does correspond to something that covers the entire space, lower dimensional regions and everything. Okay? But it's interesting that even though we didn't know about them beforehand, we didn't want them, we didn't think about them, some other kinds of diagrams are forced on us by the picture if we want to maintain this idea that the whole space is covered. Okay. Now, any guesses? What's the physical interpretation of these curves? It's gravity. Okay? In the same sense that the trace phi cube theory is gluons, colored, right? This is what you get from uncolored particles that can interact with the colored ones. Where have you guys heard these words before? Even if you start with only colored particles, inevitably, somehow, you're forced to have the uncolored ones. That's what you learn in your first string theory course. Okay? That even if you only begin with open strings, closed strings are forced on you. Right? But here we're seeing it in a way that has nothing to do with fancy schmancy string theory. It's just drawing pictures, right? Recording curves on a surface. It just tells you, I am missing some curves, right? There's a hole in my fan. I'm missing some curves. Please fill me by adding more curves to the surface, which include these closed curves. And who are the diagrams that include these closed curves? Exactly, those triangulations are dual to Feynman diagrams involving uncolored particles. In fact, let me tell you what the general rules are, and we won't talk about this at all for the rest of the lectures. This is just to give you a sort of a teaser that gravity is in this story too. Okay, that there are these sort of lower dimensional parts of the fan that include these closed curves, and that's also part of the story. We won't talk about it in the rest of the lectures, but just as something for you to play with. Let's do a little bit bigger. Well, let me tell you what the rules are. So, including closed curves is equivalent to dealing with the following Lagrangian. So now I'm going to tell you what the actual theory is that we're dealing with. Okay, it's going to be, we have our colored particles, but I'm also going to have an uncolored particle, sigma. There's no trace here. Sigma doesn't have any color. All right? But there are going to be three interactions that we're allowed to have. One of them is G trace phi cubed. That's what we talked about. There's going to be something that's like a self-interaction for the sigmas, G sigma cubed. And there's going to be a mixing, let me call it, I don't know, mu, kappa, between phi and sigma, trace phi and sigma. Okay? So it's not an interaction, but a mixing between phi and sigma. So that means in this theory, the kind of diagrams that you're allowed to draw, and apologies ahead of time, but there's simply no way to draw the diagrams in this theory without it looking slightly obscene at some points. Okay, so you're just going to have to forgive that. And if you don't see it, then good for you. That, I'm very happy for you. Okay? But for example, I can have, so what are these interactions? So I have this interaction. That's the trace phi cubed. I have this interaction. And I have this mixing. Okay? That's the problem. And so that's trace phi sigma. And for example, I can have things that look like just to give an example, I can have things that look like this. Okay? So what is this? This is something that's a double trace interaction. It's double trace because these guys just are one trace and this guy is another trace. Okay? But there's a contribution to it which is from mixing through the exchange of this sigma. An extreme version of this is if there's just one thing on one side. Okay? So that's what we're just that's just what we're just talking about. The double tracing that we're just talking about, the diagram with a single delta in it. Okay? So you see it's one lower dimensional. So the typical diagrams have two propagators. So that's one kind of Feynman diagram. Those we're talking about already. But there's also the diagrams that have one propagator in it, this one, and that's exactly the one that's associated with that missing direction delta. Okay? But if you want the higher examples, you would find that there is a lower, if I went to this example, it's a four-dimensional fan, but there would be a lower dimensional, three-dimensional part of the space, which is missing, that if I add back the delta, I would see that that part is exactly tiled by which diagrams. Oh, and what do these look like as diagrams? I mean, this would look like exactly the sort of diagram, in this case, exactly the diagram that we had talked about. You see, my rule is maximal set of non-overlapping curves. Once I draw that curve, I'm done. There are no other curves I can draw. So it's not always true that it's the same number. When it was just the trace phi cube theory, it's always the same number of propagators. But once I allow myself to put closed curves, the number of propagators can change, right? So in this case, if I add this one, I can't add any more, right? And so that's why the diagram that this corresponds to is that guy. Maybe I should have said more explicitly, who are the surfaces that are associated with these pictures? This is associated with the simplest surface, that, okay? And here there are no extra variables, no curves, nothing else that I can do. This guy is associated with this surface, where, now, when you want to imagine these as external states, the idea is if you have a puncture, I'm going to imagine putting a little circle around the puncture. Putting a little circle around the puncture means that I'm not allowing myself to have anything hit the puncture. Okay? So that's it. Okay? So I'm not allowing myself to have anything hit the puncture. So if I didn't do that, this would already be a one-dimensional surface because I could allow myself to add one more propagator there. Okay? But, sorry, and this is, that thing is not there. So if I didn't do that, I could allow myself to put this propagator there, but I'm just forcing myself to not allow that. Okay? And then there's no curves that I can draw on this surface. Okay? So that's what corresponds to this vertex. What about this one? This one corresponds to a surface which is a sphere with 3 punctures. Okay, now if I have a sphere with 3 punctures, this is already by itself a 3-dimensional surface. Okay, it's a 3-dimensional space. I can draw curves, all these curves. That's a triangulation. Is this triangle and a triangle around the back? Okay? So that's one of the examples that you will discover if you did the exercise I told you to do. It's a triangulation with 2 triangles. However, if I take this and I again demand that there is nothing that can cross these guys, so I put a little circle around every one of them, then there's nothing left again. Okay? What does that correspond to when you put a little circle around the punctures? Remember, when you have these punctures is exactly when we had this funny business with the plus and the minus, right? When you have the plus and the minus, there's always this symmetry plane that divides the two of them. Okay? So putting a little circle around the puncture in the fan means restrict yourself to the symmetry plane. Okay? So you just go down one dimension for every puncture. Okay? And you have to just live on that symmetry plane. And now the claim that I'm making is that if you take every diagram that you could make from this theory, you can interpret every diagram as a particular triangulation with the rules now that we've described. So I'm allowed to include closed loops, for example. And every one of those triangles, every one of those Feynman diagrams corresponds to a cone that lives somewhere in the fan. Okay? Either top dimensionally, which is what the trace phi cube ones look like, or on these lower dimensional surfaces, which get completed with these extra interactions involving the uncolored particles in the way that I described. Okay, so that's the sort of combinatorial generalities about the fan. And when we come back, I'll tell you a couple of more things, general things about the fan before we launch into the second part, which is how to explicitly characterize the fan and use it for describing what the amplitude is as a sort of whole single object. All right, thanks a lot.
All right, so now we go for lunch, and we should be back at 2 p.m. for Nima's colloquium.